Hello, this is Bob Lessig at Johns Hopkins. We will examine dynamic programming in this short lecture. Look more at the process and don't be too overwhelmed. Our objectives are simple: be able to explain dynamic programming in terms of this path graph exercise. And then look at a path graph and then produce the alignment. Our goals here do not include replicating the path graph and scoring, but rather appreciating what goes into a pairwise alignment algorithm. So here's our exercise. This is the alignment we want to optimize. They are DNA sequences because DNA sequences are easier to work with. And our rules are going to be simple: +1 for a match, -1 for a mismatch, and -1 for a gap. First thing we do is draw a graph. Actually, more of a grid on a simple graph paper. And on one axis, we put one sequence, and on the other axis, we put the other sequence. And our goal is to find the best path, beginning in the upper left and ending in the lower right at the end of the sequence. First, we'll look at how diagonal lines score. A diagonal path can be a +1. You see the arrow is a match because it's an A to an A. Or -1 for a mismatch. That arrow is in the A to T region. Here's what's not so intuitive and something I want you to discuss in the discussion forum. Horizontal and vertical lines always score -1 because they are gaps. And the horizontal line, T aligns between the G and the A on the left sequence. And in the vertical line, the T in the left sequence is between the G and the A. So you put a gap between the G and the A in the top sequence. To think of it another way, horizontal or vertical lines allow you to skip a letter in one of the sequences. Again, maybe not so intuitive. It might make more sense when you see the final result. So what we do is we keep extending from the beginning. So the G to G match is a +1, and the horizontal and vertical lines are -1 paths. And then you keep going and you find the best path to each point. And you incrementally extend, and I just showed part of the scoring mechanism. It's very much like MapQuest or Google Maps. Instead of finding the fastest route between 2 points, we're looking for the highest scoring route. And in the end, you find the best scoring path. And the best scoring path in this particular graph is here. There really are 2 equally scoring paths. See if you can find the other. Okay, so with this path, what's the alignment? We see that the G and the A align. And then the T in the left sequence aligns between the A and T in the top sequence. So we put a gap between the A and T to fit that T in. That's what I meant by the vertical line. And what that does is that puts you on a diagonal where the TACTA and TACCA, so it puts it on a fairly high scoring diagonal. So a quick exercise is to look at that and say, well, what is the score of that alignment based on our scoring system? I'll leave that to you as a discussion problem. Now, we used a very, very simple scoring mechanism. But typically, rather than +1 for match and -1 for mismatch, especially if you're using proteins, we'll use substitution matrices. So you see the scoring is a lot more complex, but the goal is the same. The goal is to find the best path from the upper left to the lower right. So rather than summarizing, I'll throw out some questions for the discussion. First of all, why are vertical lines and horizontal lines gaps? If that's not clear, bring it up in the discussion forum. Are there any other alignments in that exercise that score equally to the one that we came up with? Finally, let's relate what we see here to global and local alignment. How would that differ looking at this exercise? Hope you find this helpful, and good luck.